All right, so today, kind of left off with some examples last class. We'll jump in and do a lot with Excel today on confidence intervals. So make sure you can see it. The file we'll be using is confidence intervals example. And then after we get through that, if we have time, we'll kind of work into the CI grade data, try to give you a little bit better understanding of what we're doing with these confidence intervals. So we left off, kind of had this, let's look for a more general form. There we go. Right, we know this is how we're building our confidence intervals. We said the standard deviation of our sample means, there's usually like this extra step we have to do, which is if we want to calculate that first and then plug it in, or we can just plug everything into one equation, and either way we'll get the same answer, right? So this was kind of the setup. We had these different examples where we see a sample mean based off the sample size and the original variance and whatever confidence level we want, right? So that'll be specified by our alpha. We kind of worked through, we find the z-score that gave us half of alpha on each side of our interval. We then calculated that standard deviation of our sample means, and then it's just a matter of plugging everything into that confidence interval equation. And we talked a little bit about interpreting the confidence interval. So here we have our three kind of conventional levels, which are the 90, 95, 99%, which correspond to alphas of 0.1, 0.05, and 0.01. So these will be some pretty common levels that we look at. So let's open this confidence intervals example. I've got a lot of things filled out here. Let's go to the known standard deviation and proportion sheet. So it's the second sheet, I think, in the way I uploaded it. So I'm going to zoom in here a little bit, and then we will delete a little bit, and I'll kind of rebuild some of it, mentioning what we're doing along the way. Okay? So don't worry about this for today. We're going to delete the z-value and this lower and upper bound I had down here. I'm not going to delete any of this. So this is kind of a weird scenario where, so I have this data set, right? It's all these different schools. It's their male and female undergraduate enrollment, their total enrollment, and then a variable for 1 if the enrollment's over 10,000, and 0 if it's not, okay? So I don't have every school in this data set, but I have most of them, right? So let's assume that we're starting off this example, because the examples we've worked to up to this point, we've been given a known population variance, right? So let's just say somehow we know the population variance. In this example, I calculated it using the data, but that's not really accurate because this isn't truly population data, okay? So let's assume, maybe if you see this equation and get confused, just think about it as 1, 2, 3, 4, 5, 6. So 68, 1, 2, 3, 1, 2, 3. So let's just assume that we're told it's 68 million for some reason, okay? That's just given to us. We know the population variance. Don't worry about this cutoff. This is for something we're going to do later on, just kind of working with the same data. So if we want to kind of move this around so that we're not dealing with that today. What I did was I took this data set and I found the mean undergraduate enrollment, right, just using that average function. I found the sample size by using that count function. Remember, it counts the number of observations, just goes through the data. So really you could think about this is our n, right, our sample size. So we've got our population variance, our sample size, our sample mean. The only other thing that we needed when we were doing these confidence intervals was alpha, right? And then we could construct some confidence intervals. So I'm going to show you the preferred way of doing this, okay? I'll kind of show you a couple different ways, but the first one I'll show you is probably what I think is the easiest for you guys. Okay? So one of the things that we were doing, let's see, I'm going to switch over to the dot cam real quick. Can I give us a reminder? It wants to switch over. There we go. So kind of a reminder of what we were doing. When we were looking up that z-score, we wanted the z-score that gave us alpha over 2 on either side of that distribution, right? Or a total of alpha kind of in those tails. So usually how we were doing this was, I don't know, let's say we were doing the 90% confidence interval. alpha would be 0.1, divided by 2, 0.05. We looked up 0.05 in the tail, and it gave us that z value. Sorry, we looked this up in the standard normal table as the area in the tail, and then found the corresponding z value. So that's what we're going to do in Excel, so we don't have to use that kind of pre-built table. What we can do, if I can get this chair to, there we go. We actually have already done this, right? So we did this when we were just talking about that weather data, where I could look up z-scores, or I could look up the area I want in the tail, that inverse transformation. Right? So norm.s.inv says use a standard normal distribution, right? Oh, sorry. That would help if you guys could see that. I'm just going to leave this up, so hopefully when I switch back and forth now, it won't do this. All right. So I can use that norm.s.inv. It says use the standard normal distribution because I'm trying to find the z-score, right? And work backwards, work in like the inverse, work in reverse if you want to think about it that way. All we have to do is tell it the area we want in that lower left tail. Well, what was the area that we wanted in that lower left tail? Just alpha divided by 2, right? So alpha, just click on the cell that has alpha in it and divide it by 2. Right? This should return to me that z value that gives me what? 0.05 in each tail. Now the problem is the way that this function or this formula works in Excel is it always looks at that left side. So it's going to look up, okay, what z value gives me 0.05 in this lower left tail. So when we have these really small alpha values, we're always going to be getting the negative z-score, right? But we know that really there exists two, but that's kind of already, we go back here, it's kind of already built into the confidence interval equation, right? Adding the z-score, right, we get the upper bound, and then when we subtract it or use the negative value, we'll get the lower bound, okay? Excuse me. So I'll get the negative value, but to make it easier when I'm constructing my lower and upper bound, I really just want the absolute value, right? I want to just plug in the absolute value, ignoring that negative sign. So I can do this two ways in Excel. The first is I can just use this ABS function, which just takes the absolute value. It essentially drops the negative sign for me. So I can do it that way, right? And now it's kind of nice because I've referenced the alpha cell. So when I copy this down, it updates it to the new alpha. So I'm going to try to construct 3 confidence intervals here. One, here, I'll insert a column here just to kind of give you a little bit of better of an idea. So we think about what levels of confidence this is. This is the 90, 95, and 99% confidence levels, right? So I'm building 3 different confidence intervals here. Now, instead of just taking the absolute value, there's another way I could have done this. Right? So if we think about, I want to find 0.05 in that lower left tail, it will give me the negative z-score. I think it was like what, negative 1.644 something. So I know that, right, that z-score value is 1.644, so I took the absolute value. Or what I could have done, if I wanted to just get the value, but the positive one, well, if there's 0.05 in the upper right tail as well, what area would be to the left of this z-score? Just 1 minus that, or 1 minus alpha over 2. Right? So instead of using that ABS function, what I could do is, oops, go over here, get rid of my parentheses, and then just do 1 minus alpha over 2. And if what I'm telling you is correct, sure enough, we get the exact same value. Okay? So either way is fine. Right? Either way will get me that, just the absolute value of that z-score I need, that z value I need. From here, it's really just using Excel to kind of be a calculator. Okay? So one of the other things that we needed was the standard deviation of my sample means. Okay? So standard deviation of sample means kind of put up here. And you could really put this anywhere. If you're trying to follow along, you can put it kind of over here somewhere. We're just going to reference the value that's in this location. So the standard deviation of my sample means is the square root, so SQRT, of the original population variance that I sampled from, of the data I sampled from, divided by my sample size, which, I don't know why, I hate when it does this, but it's going to be what? Cell M3, right? The one right above it. Okay. Any questions up to this point? So we're basically just doing what we did by hand, but using Excel to kind of be our calculator up to this point. So we get the standard deviation of our sample means. Now it's just a matter of putting this, kind of using Excel to do this equation, this math for us. So the lower bound will take our sample mean, right? That's what we're building our confidence interval around. We'll then subtract our margin of error, which was just that Z value that gave me alpha over 2 in the tail, multiply by, well, that was the number of standard deviations away from the mean I had to go. Here's the standard deviation of those sample means, right? The distribution I'm looking at. So I've really just used Excel to be a calculator for me here. Okay? And I get my lower bound. Well, if I want to copy this down, that's great because I want to, to build the 95% confidence interval, I need a new Z value. But I'm still building it around the same sample mean, and the standard deviation of my sample means hasn't changed. So I'm going to go in here, select the sample mean, hit F4, select that standard deviation of my sample means, hit F4 or Command T on a Mac. I've now got those frozen. Right? So now when I copy this down, it's still using the same mean and standard deviation of my sample means, but it's updated that Z value. Any questions on anything there before we keep moving? Okay. If I want to do the upper bound, well, I'll actually show you kind of maybe an easier way. I'm just going to, so if I drag this over, there's going to be a problem, right? Because it updates that cell over one column. I could freeze it and then unfreeze it, or if you click on a cell so that you can see the cell references, like I double clicked on it, highlight that, copy it, and you can use the shortcuts, right? Control C, or I don't know what it is on a Mac, probably Command C. I'm going to hit enter to get out of the cell, because if I don't, notice, if I just click in another cell, it puts that as the reference, it erases it. So I didn't want to do that, so I'm going to kind of undo that. Hopefully you know the undo button on your laptop. It's just Control Z, or I'm guessing Command Z on a Mac. So I copy this, I hit enter, and it takes me right out of the cell, or doesn't take me out of the cell, it kind of hides those formulas again. So then I go to the upper bound, I'm going to paste what I copied, so it should be the exact same thing, which is what the upper bound equation should be, except for instead of subtracting that margin of error, we add it. Right? So now I've got the same thing, but I'm adding that margin of error. I can copy this down, and I've got my lower and upper bounds, right? So I've got 3 confidence intervals here. Okay. Now, what we said is, kind of the intuitive thing is, yeah, if I can tell you with 90% confidence that it's in between, I don't know, 10 and 20, with 99%, maybe I could tell you it's between 0 and 30, right? I just make my confidence interval wider, and that's a higher level of confidence. And sure enough, higher levels of confidence, my lower bound is getting lower, and my upper bound is getting higher, right? So that interval is getting wider there. So that's one of the things we talked about last class as well. Higher levels of confidence means I want a smaller area in those tails. How do I get a smaller area in these tails? I have to use a larger in absolute value z-score, or Z value. Okay. So when I have a larger Z value, right, that's part of the margin of error. So if Z goes up, I'm adding and subtracting a larger value to my sample mean, and sure enough, my confidence intervals here get wider. Okay. Just kind of revisiting some of the things we talked about last class, but seeing it play out in Excel. Okay. Are we okay up to this point? Yeah. Okay. I'm going to show you another way that you could have done this. So I'm just going to copy and paste this table below it, and then get rid of these values. Okay. And in fact, I'm actually going to eliminate this intermediate step. I'm going to delete that Z value and show you we can do this all in one cell. Okay. So before I had broken this down, I found the z-value here, I found the standard deviation of my sample means here, but the other form of the equation, so if we just plug everything in, right? I don't have to calculate this intermediate value. I can just plug it into that equation, right? So I could have done this all in one cell. So what would that look like? Well, I know that I'm going to build the lower bound around the sample mean. So I reference that sample mean. I'm going to subtract. Well, I need the z-value. Well, before I'd calculate it in another cell and then reference it, but I can do it all in one cell. Use that norm.s.dist. Right? Sorry, not dist. What am I doing? INV, right? I know the area I want in the tail. I want to find the z-score that would give that to me. So that probability of the area I want in the tail was just alpha divided by 2. Now I could have used the absolute value formula here, or I said I could do 1 minus alpha over 2, and it will do the same thing for me because it's a symmetric distribution. Then from there, I could multiply by the square root of my population variance divided by my sample size. So I don't have to break this down, right, like I did here where I calculated the z-value in a different cell, and I calculated the standard deviation of my sample means in a different cell. I can put it all in one. Right? Now, you know, is one way better than the other? I don't know. Not necessarily. You can still get the correct answer. But if you do it this way, it's a lot harder for you to see, like, if your z-value equation isn't working right? If you're getting like a weird z-value, or if, you know, this is, you know, not positive, right? You can't really see that here. Like if I forgot to do 1 minus, I wouldn't see that the z-value is actually negative, and I don't want to use a negative z-value. I just want the value, right? The absolute value of it. So, you know, it's a little bit more hiding things behind the scenes. If you do it the first way we did it, you can kind of see step by step what's going on. But this way works as well. So notice we get the exact same lower bound. It's because we just kind of compiled everything into one cell. So when I copy this down, the only thing I want to change is alpha. So I'm going to freeze everything else. So F4, F4, hit enter. Whoop, what did I do wrong? Well, I don't know. I think everything's good. I might have had a parenthesis issue. All right. Copy that down. We get the same lower bounds. Same kind of thing to get the upper bound. Easiest way probably, I'm just going to copy it, hit enter to get out of the cell, go over here and paste it. And the only difference in my upper bound equation is I add that margin of error. Now that I add that margin of error, I'll drag that down, and I've reproduced the same exact thing. Right? So it's really the same process, just you're not calculating these intermediate steps in the second one. Okay. Any questions on? I went through that kind of quick, but it's really just we're putting everything we did before into one cell. Check. Okay. So we're okay with this? All right. I might hold off and show you something at the end. Yeah, I think we'll leave it there for right now. Okay. So if we're okay with that, so hopefully, you know, now we kind of have a little bit of an idea about how we can build these confidence intervals in Excel. So one thing I don't want you to do, I mean, if you can use it correctly, that's fine. There is a built-in confidence.norm equation. So if I tell it like, you know, my alpha, my standard deviation, the problem is, so the standard deviation here would be what? The square root of my variance. I move this out of the way, you can see that. Right? And then what's my sample size? So I go up here, select my sample size. What this confidence.norm does, right, is it's trying to give you kind of the lower bound. The issue is the standard deviation you actually should be using, right? The alpha is really, I think, the area in the tail. So if I change this to 0.05, I notice I'm starting to get something, you know, that looks closer to my lower bound, but it's still not quite correct. And that's because the standard deviation I should be using, if I remember right how this works, is up here. Well, now it's 145. Well, this is really what this is telling me. Is this the distance I should go to the left and right of that sample mean? So I think now if I take the mean and I subtract, well, what was it, L 23? That's still not, oh, isn't that right? Oh, because I was messing around with this alpha, sorry. So it's still not right. So I honestly, I never used this version of it because what it's trying to tell you is kind of what that margin of error is. The problem is, you know, what I was doing here was using something like the population or the, actually, this should work if I do this. Hold on. I was going to show you how to use this, and I forgot to take the square root of that. There we go, all right? So I put in that standard deviation, the alpha, and the sample size, and it's telling me the distance to go to the left and the right of the mean, so I can use that formula. The only reason I don't like using that, and you can see I don't often use, I usually kind of piece it together like I did here, is one, it doesn't teach you how to use those formulas kind of by hand and how to, probably going to help you for the exam, right? I mean, you can use Excel in the exam, but this is going to be, you know, a little bit more black boxing, a little bit more difficult, and you could easily make a mistake. So if you were to do it by hand, at least when you're entering the functions in or formulas in like this into Excel, you're also getting just used to what those formulas mean, what the different things in the formula mean. If you use that confidence.norm and you use it correctly, like on the next Excel assignment, I'm not going to mark you down. But I don't expect you to know how to kind of use this because it's a little bit misleading. It really should be like named, I don't know, margin of error.norm or something, right? Like it's giving you that margin of error. And also once we start moving to sample proportions and then sample means where we only have a sample variance, I think using this in Excel just starts to cause a lot more confusion, especially once we're looking at the sample proportions. So the best way to get used to doing this is probably how I have it set up here. But I know that some of you, maybe this is going to fall on deaf ears and that people aren't going to be watching the videos that might do this. But you know, if you just Google how to do confidence intervals, you might find a resource that tells you how to use this. But I just don't think that it lines up with teaching you how to correctly think about building these confidence intervals. And so I am not going to be using this formula for the context of this class. Once you get out of this class, it's fine to use this. It's just a little bit, just hides a little bit more things, and I think it can cause some more confusion. So they want to make sure I mention that before we kind of move on there. So I'm going to get rid of that there. Okay. All right. So the next file I wanted to look at is this CI grade data. Okay. So I don't know. I'm saying all these things and I'm walking through these examples, and I haven't really shown kind of the mathematical proof behind why or kind of supported with data. I mean, we have kind of the mathematical proof as to why. We got the intuition of it, but I really want to hammer down that in practice this would work. Okay. So last class we started talking, or I kind of laid out this example where I was like, oh yeah, if we looked at all the sample mean values, we know they should be distributed around the population mean. You know, I find that number of standard deviations the way I want to go. Every sample mean I see here, if I were to build my confidence interval around that sample mean, it includes the population mean value. But then every single sample mean out here, when I build my confidence interval around that, it won't include that population mean. And that's why we said, well, look, we know that if we wanted, say, 95% confidence interval, we can find the number of standard deviations the way we need to go using that standard normal distribution. So what should be true is that if I took like an infinite number of samples and built confidence intervals around each sample, that 95% of the time, my confidence interval would include that population mean. 5% of the time, the confidence interval I built is going to be wrong. It's not going to include that population mean. So I did this example in Excel where, and I'll walk you through it because we're going to have to introduce a new function we haven't seen yet. But I had all this data, right? Let's see how many. So 431 different business statistics students, and I had what their grade was kind of rounded to the integer, right? So these all represent different students. These are their different letter grades. Okay? So I have population data. This is the population data set for students that I've taught, right, in my stats courses. Actually, that's not quite right because I didn't work in the last semesters, but pretty close, right? We'll assume it's the population. So I've got this true population mean. So this is the true kind of population mean. I'll widen this a little bit. And then I can also calculate what that true population variance is. So this is a weird situation where I have the population data, but I want to prove to you if we took samples from it that all of these things would hold. That 95% of the time, the confidence interval I build will include that true population mean. So what I do is I have my sample size over here, right, using that count function. So we can kind of think about this is my n. Or actually, no, sorry, this is my total number of population. So this is, whoops, trying to cap, okay, come on. Keep hitting the wrong button. Now there we go. Why is this, I hit insert or something? Yeah, I hit number a lot. All right. What did I just do? All right, I don't know what I hit there on my keyboard, but so we've got our kind of population size. What I then did is say, okay, look, I'm going to take a sample, I'm going to take 1,000 different samples, all of size 50. Okay, so this you can kind of think about, this was actually, sample 1. Here's sample 2, so on and so forth. Okay, I want to build a 99% confidence intervals. Right? So for this first sample. And this part, I'm not going to expect you to know how to do, but I used a random number generator and then used a VLOOKUP formula to look up, okay, whatever student was in 374th position, put their score here. So I was randomly selecting students, and then this is going to be what their test. I wouldn't expect you to kind of do this. This is further in Excel than I want to take us in this course. But it still allows me to get a sample where I then have 50 random students. Okay, well, I can calculate my sample mean using the average function. And then based on that sample mean, well, I have my sample size. I know the alpha value. I also know the true population variance. So I could do what we just did here, just to kind of save space. I didn't calculate the z-score first, and I didn't calculate the standard deviation of my sample means first. I just did it all in one cell just to make it a little easier to look at. But this is what we just did, right, to build our lower bound. It's just that the cell references change because the sample means are in different places in this worksheet. So this will give me my lower bound, and it references that alpha value I had up there of 0.01. It also gives me my upper bound, right, just adding that margin of error. So for the first sample, with 99% confidence, if this was the only thing I could see, this first sample that I took, I could say, well, with 99% confidence, the true mean is somewhere in between 74 and 84. I go up, sure enough it is, right? So that one did include the population mean. I then take, notice here is kind of generating, I have a random number generator in here as well. So it's randomly generating another 50 numbers. It's just kind of hiding them here. I just wanted to show you that I was generating random numbers in this column. So it's getting 50 different test scores, right? Another, random 50 test scores. Now for that sample, I calculate the sample mean. I build my lower and upper bound, okay? And I do this, 1,000 different times, right? We can kind of keep going off here. I have 1,000 of them. And just to prove that I had 1,000, I didn't just type the number in here. I counted kind of going to the right, so I made sure that I got 1,000 different samples, okay? So if what I'm telling you is true, for these 1,000 samples, approximately, right, 99% there we'd have, So we'd have 900, sorry, if alpha was 0.01. So we'll have, why is my brain not working all of a sudden, right? Yeah, 10, okay. So 990 of them, right, should have a confidence interval that includes the population mean. 990 of these samples, when I build these confidence intervals, should include the true population mean, and then 1% of the time I'll be wrong, right? So 10 of them should have a confidence interval that doesn't include the true mean. If it's easier to think about, since I have all this referenced, I could do alpha of 0.1, which makes it a little bit easier to think about. There's 900, right, that are going to include that true population mean, and then 100 that won't, okay? So we go down here, and what I did was, and this is where I might expect you to use this, maybe not in the next assignment, but eventually we'll use it kind of towards the end of the course. It just makes our life a little easier. So there's a function in Excel called the if function, right? So before we look at this, let's go back to the other worksheet that we had. So what I could do is run this check to say, okay, is a certain value within the confidence interval? So let's say, I don't know, the check value I'm going to use is 19,500. Okay? So here I'm going to use an if statement. And the way that if statements work in Excel is I say, okay, check to see if this is true, comma, if it is, do this, comma, if it's false, do this. Okay? So the test I want to say is, okay, is that value that I have here, 19,500, is this outside of my confidence interval? Is it greater than my upper bound? Because if it is, well then that value can't be one of the true population means because it's not in my confidence interval, at least at the 90% level, right? With 90% confidence here, it's pretty easy to see, well, 19,500 isn't in that interval, right? So it shouldn't be one of the true, 90% confidence I could tell you it isn't one, the true population mean, okay? Because it's not in my interval. So, comma, if that value of 19,500 is greater than my upper bound or outside of my confidence interval, I want to put in this cell, I want it to read not an interval. And if that's false, and it's not greater than the upper bound, so it's within my confidence interval, I want to put the word that it's in the interval. Right? And that's what I want to display in this cell. Now, there's a problem with what I did here. If I hit enter, anytime you want to put text in a cell, you have to put these quotation marks around it. So now what this if statement should do is, if that 19,500 value is above the upper bound, it's outside the interval. But if it's not, then I want to return that it's in my interval, right? It's in my confidence interval. So, sorry, I need to freeze this, right? Because I want to keep using that same value, check that same value against the next two confidence intervals as well. So I can copy this down. And this one, it's kind of easy to see a visual check, right? Because, okay, yeah, 19,500, not in this interval, not in this interval, but it is in that 99% confidence interval. Okay. So that's just kind of a rough, like how that if statement works. Now we can make things a little bit more complicated. First of all, are there any questions on that? Do you want to see any of that again, or one that explained a little bit differently? Okay. And we could play around with this value if we wanted to. Okay, so that one's not in any interval. I don't know, 1,800 or 18,000. It's in all the intervals, right? We could play around with that value. So what I did in this other file where I had these 1,000 different samples and basically 1,000 different confidence intervals, right, is I used this if formula to say, okay, look, and I had to check two things, right? I said, if that true population mean, if it's greater than, sorry, actually, I think what I did was if it's less than my upper bound, then do this. So I kind of put in two if statements here, right? Now, I'm not going to expect you to kind of use these nested if statements, so don't think that you're ever going to have to do something that's this bad. You would only ever have to use it kind of one time, like I just showed you in the other file. I'm not going to expect you to know how to do this, but what this statement does is essentially it's checking to see if the population mean is less than the upper bound and greater than the lower bound. So checking to see, is it in that interval? If it is, it's telling me a 1, right? So between 80 and 73, 79.8, the true mean, is in that interval, so I put a 1. 78.9 is in this interval too, so I put a 1. It's in this interval too, so a 1. It's just outside, I think it's 79.8, so it's just outside this confidence interval, so there's a 0 there. So what I then did was, okay, this is a 1, 0 for whether or not the true population mean was actually in that confidence interval that I built around that sample mean. So so what I did here is I used that sum function to count this, or add these all up, which will basically give me the number of times that this was a 1, or the number of times the population mean was in my confidence interval. Okay. If I then kind of have 1,000, right, that's my number of samples, then this is telling me, this is kind of like the, well, I'm going to leave myself a little more room here. Percent of confidence intervals that include true population mean, right? So I'm just taking the number of times that the population mean was in the confidence interval, divide by 1,000, and then I think I multiply by 100 to make it a percent. So notice, these random number generators, every time I click on a cell and hit enter, it randomly generates a new number of numbers. I'm going to close that. All right. So every time I click on something, it's generating kind of new random numbers and basically giving me like 1,000 different new random samples. So the numbers change around a little bit, but notice that percent of the time that the true population mean was in my confidence interval just floats right around 90%, right? That one's a little bit high, that one's a little bit higher, but right, notice right around 90%, okay? Which, that's what I have my alpha set at, right? That 90% of the time, my confidence interval will include that true population mean. Now, I'll be wrong 10% of the time, but, being right 90% of the time is pretty good. So, one thing to point out here is it's not exactly 90. And the reason why is because in theory, the way that we would actually have to, we would get exactly 90% is if I had an infinite number of samples, right? I'm going to be, there's still some randomness to this because I still technically only have 1,000 samples, right? If I were to do an infinite number, I would get exactly that alpha as kind of the, portion of times that I was incorrect, or that my confidence interval didn't include that true mean, okay? So I don't know, I think this is kind of I like this because I think it shows, if I was taking all these sample means and I did, this 1,000 times, it really is holding up. 90% of the time I'm going to be correct, okay? The way I have this set up is kind of nice too, because you could change the alpha to 0.01, it updates everything. Now notice I'm right around 99% of the time that I am including the true population mean in my confidence intervals, okay? Any questions on any of this? And if, I don't know, I should say here also, if you're interested more in Excel for other classes, or I don't know, maybe you want to build something for your job, I don't know. But I use Excel to do a bunch of different things, and my girlfriend makes fun of me all the time for it. So I actually just built one for selecting teams for the tournaments. And it's got a bunch of other stuff that's real nerdy. But I think if you ever have questions like how can you use a random number generator, what does this VLOOKUP do? VLOOKUP is very powerful when you're dealing with large data sets. I would imagine accounting majors, if you want to work across different worksheets, this VLOOKUP could be really useful to look up different clients or to different, individuals' names. So there's some, I will admit this CI grade data, there's some stuff going on here that you don't have to fully understand. This was more so to kind of prove to you with some data that what I was saying, using these pictures last class was going to hold, okay? The one that you should know how to do everything in is that confidence interval examples, or this is going to look more like what you're probably going to be expected to do on that next Excel assignment, okay? Which I probably won't post after class Friday. I'll probably hold off until next Monday, and then the due date will be like another 2 weeks off. So we got quite a ways until we're really going to be completing that Excel assignment. But this will be the very first thing on it, All right, we've still got a lot of stuff to get through before we have enough to really get that assignment out there, but this will be what it looks like, okay? Any questions on this? All right, so that's pretty much what we want to do in Excel today. We've got 10 minutes, so let me think what I want to do. I think I'll explain this and we'll probably just work through examples next class. So, you know, if we know that the distribution of sample means is normally distributed, but we also said that the sample proportion will be normally distributed as well if we get a sample size over 30. So we can build confidence intervals for the population proportion as well, right? Just like we did for the population mean. It's going to be a little bit different. Okay? So for the population proportion, we said the mean of that distribution was whatever for our sample proportions, what we said is the mean of that distribution, or where it's centered around, should be whatever the true population proportion was. And most of the examples I think we were using was like flipping a coin. We also said the standard deviation of our sample proportions was the square root of the original population variance times 1 minus the original population variance over our sample size. Well, here's where we run into a problem. Because if we only have one sample and we don't see what the true population proportion is, right? That's why we're building a confidence interval. We can't actually see what the true population proportion is. The way that we're going to kind of sidestep this, because we'll need that standard deviation when we build our confidence intervals, is we're going to use the sample proportion we see to kind of estimate, that's our best guess of what the population proportion is. Okay? So it's going to look a little bit different than what we talked about with the distribution, because the true distribution of our sample proportions, this would be the standard deviation, right? But we aren't able to observe the population proportion. We only have a sample, so we're going to get our best estimate using the sample proportion we see. Okay? But from here, we can construct a confidence interval just like we did for the mean. So if I try to make these comparisons, right, think about what we were doing before. So we had this, right? When you look at a sample proportion, and you're trying to build a confidence interval for where the true population proportion is, well, I'm not going to build it around the sample mean. I'm going to build it around the sample proportion I saw. I still know that I can use the standard normal distribution, right? Because I said, as long as I have a sample size over 30, the distribution of my sample mean and sample proportion will be normally distributed. I'll then multiply by the standard deviation of my sample proportions. So it looks really similar to what we were doing before. The only exception is if I want to do this all at one time and I don't want to calculate the intermediate step, the standard deviation of my sample proportions is going to be this. So I could plug that in down here. Right? And now I've got my confidence interval for my sample proportions, right? Either way. So I can calculate the intermediate step and plug it in, or I can do it all at one time. So very similar to what we're doing before. Now remember, the standard deviation of our sample means was the square root of the original variance over our sample size. And really what the numerator here is capturing is really like the variance of the original population proportion, although it's an estimate now, right? Because we can't actually observe the true population proportion. So we have to use our kind of best tool available to us, which is what we see from our sample. But really from here, it's the same process as what we were doing before with the sample mean. Nothing else is going to be any different, right? So let's go back here, right? And this has to be, we'd have to make sure that this is true, that we have, if we have a really low probability of something occurring, we need a larger sample size, right? Or if we have a low sample size, the only way that's going to be okay is if we have a pretty high population proportion. So I'll never try to trick you with this. This is just something that we would kind of need to hold kind of, if you're kind of going to the next level of statistics, this is something that you'd probably want to recall and remember. But for most situations, we're going to have high enough sample sizes to where this isn't an issue, right? We've got a lot of data most of the time. So here's our confidence interval equation, right? And this is where I can correctly call this term the margin of error. I said I was going to do that for sample means as well, just because it's easier to talk about talk about it, but to be technically correct, the margin of error is really referring to the what we add and subtract when we're dealing with sample proportions. Okay, but for this class and for what we're going to do, it's easier to talk always about what we add and subtract to our sample statistic as being the margin of error. Okay. Any questions over any of this before I? Okay. So I think I'll end there. I just want to introduce that idea, and we'll start picking up where we work through some confidence interval examples on Friday. So we'll work through a few confidence interval for sample proportion examples, and then we'll do some work in Excel as well for proportions. So we'll be dealing with, let me see. I want to go to the Excel. We'll be dealing with this confidence intervals example Excel file again, and that's where we'll be using a sample proportion and building some confidence intervals for a sample proportion. Okay, it'll look really similar to what we did today. Just, you know, a little bit. Oh, no, I already switched the camera, so it's going to look very similar. It probably doesn't matter. I mean, I probably just end it here, but it's going to look very similar. We'll go to the .cam one last second to end this. It's going to look very similar, but we're going to have slight differences in the equation, right? We're calculating the intermediate values, right? The standard deviations of our sample statistic. It's just going to be a little bit different, but we're still using the standard normal distribution, so it's going to look pretty similar. Okay? So we'll pick up with that on Friday, which is also when that Connect assignment is due. So if you have any last minute questions over the next couple of days, make sure you get those to me. Hopefully, you know, not Friday at 10 o'clock at night, right? Okay. So enjoy the nice weather today, and I will see you guys on Friday.